So today we're going to go over the top of page 13. We're just going to talk about scientific notation here because we are going to get ready to do some math that might end up with some big scientific notation numbers. So let's go ahead and figure out, well, what is scientific notation? And feel free to summarize this definition here at the top of your page. Really when it comes down to it is it's a way of writing numbers that are way too big or too small, or very big or small. And I like the full definition because it's all about making things easier. I don't want to write 100 zeros or even like 6 or 7 zeros if I don't have to, especially if they're not significant figures. So this is a way of scientists getting rid of some of those non-sig fig zeros that we would have in standard form. And I like that part of this definition being there too, personally, because that's what we call kind of normal numbers, standard form. Our scientific notation is always going to be in this form, some number A, and then we have the times 10 part of the scientific notation. That's how you can always tell when something is scientific notation. And then on that 10 is going to be some other little number B. And for ease of communication, as we're talking about this scientific notation, that number A that's before the times 10 is what we call the coefficient of that scientific notation number, or the base of the scientific notation number. And B is the exponent on the 10. So it's some number times 10 to an exponent. Now, those are the parts of our scientific notation, and right below that is an explanation with some specific instructions on how to turn a standard form number into scientific notation. And we don't have the reverse directions because once you kind of understand enough to write numbers in scientific notation, it's pretty easy to take them out of scientific notation, and we're going to practice doing examples both directions. So, in general, with scientific notation, we're going to put the decimal after the first non-zero digit and look at the rest of the digits that we've got and only keep them if those are sig figs. So like I said before, we're going to be getting rid of any non-sig fig zeros. And that becomes our base, the coefficient of our scientific notation. So at this point, after I've moved my decimal, I do tend to rewrite that as the base. And then I write my times 10 after it. And then all that's left is to find that exponent. And in order to determine what your exponent is going to be, we count how many times the decimal had to move to get from where it started in the original number to where we put it after that first non-zero digit in step 1. And however many times we had to move that decimal, that number is going to become our exponent. Now, we just need to double check whether that is going to be a positive or negative exponent. The number of times we move it is always going to be in that exponent. But if that original standard form number is larger than 1, something like 500 is larger than 1, then that exponent in our scientific notation number is going to be positive. If the original number in standard form is less than 1, something like 5 millionths here, 0.0005, then our exponent is going to be a negative number. So I can easily remember positive for bigger, negative for smaller. And that is how we're going to tell what sign to have on our exponent. If you have any special rules for deciding positive or negative, anything that you've learned previously, because I know you've probably learned how to do scientific notation before, I would be interested because this is something kids struggle with sometimes. But I don't like to tell them, oh, left if it's bigger, right if it's smaller, because we're going to move it the opposite direction when we're taking things out of scientific notation. And so I think it gets confusing there. So let's do some examples because I think that'll help make this process a little bit clearer. So I have those summarized steps at the top to remind us what we're doing. Hopefully you can still see those instructions on your page as well. So I'm going to do these 3 examples and then I'm going to have you try out some of these other 3 examples. So, in our first step here is to put the decimal after the first non-zero digit. And I say first because we should be reading left to right. So as we start at the left of our number, the first non-zero digit is this 3. So I'm going to put my decimal after the 3. And as I'm looking at the rest of these zeros, at least before I put a decimal there, those were trailing zeros. And with no decimal visible in that number, those are not significant figures. So the base for my scientific notation is just going to be 3. And then we can write the times 10 part because that's always going to be after our base. And then we're just trying to figure out what that exponent is. So now we can count how many times that decimal had to move to get to where it is. And I know this confuses some people because there wasn't a decimal in our original number, but the only place a decimal could be where we couldn't see it is kind of invisible there at the very end of this number. So that's where it kind of started, and I always have to draw these little loops to count how many times it moved. Moved 6 times, so there is going to be a 6 up here. And when we're double checking things, looking at this original number, this number was bigger than 1. It's a big number. That's 3 million. So that should be a positive 6. And we can just leave that as 6 here. We don't have to write the positive sign down. So this is our shortened form of this big long number, just 3 times 10 to the 6th. If we go across to this next example, first we need to find the place to put our decimal point, and as we go from left to right, the first non-zero digit that we run into is that 1. So we put our decimal after the 1, and now looking at these zeros, even though there was a decimal in this number, these zeros are not sig figs because they're leading zeros. Leading zeros are never significant. So the only part of our base that we need is the 1.2. And then we write the times 10 part because that's always part of it. And here we can see where our decimal started. So we can easily count 1, 2, 3, 4, 5, 6, 7 times. And so I am going to put a 7 in my exponent. But as we look at this original number, this number is smaller than 1. Which means that this should be a negative 7 exponent on our 10. So 1.2 times 10 to the negative 7th power is our scientific notation version of this number. Same kind of process is going to happen here with this one. The first non-zero digit as I'm going from left to right is the 6. These are not sig figs, but both of these zeros are sig figs because we've got a decimal up here for that last 0, and captive zeros are always sig figs. So my base here is going to be a little bit longer than before, but we've got to keep all of our sig figs. And now I need my times 10, and I need to count 1, 2, 3. And this original number was less than 1, so that is going to be a negative 3. So hopefully that isn't too bad. I want to see you finish these last 3. We can check them in class if you're uncertain of your answer. But we should end up having a negative exponent on these two because they are smaller than 1. And we should have a positive exponent on this number because it's bigger than 1. So try those out. Even if it's wrong, I'll give you a stamp, but I will not stamp you if those are blank. So let's talk them over when you get back to class. And let's go ahead and move forward to these examples where we're taking our numbers and taking them out of scientific notation. So this is easier, and I left these instructions up top just because that's what we did to find these numbers, and really what we need to focus on is counting how many times the decimal has to move. That is our exponent. So here with this first number, I already know I'm going to move that decimal 5 times. The only question really is, am I moving it left or right? And if you remember that the original number is going to be larger than 1 if that has that positive exponent, well, this is positive, so I need to move this decimal a direction that's going to make this number larger than 1. So if I start trying to move it left, oh wait, 0.1 is not larger than 1, so I'm going to move it right instead. And I need to move it 5 times, but there's only 2 numbers there to move it past. So that means after those 2 numbers, I'm going to be adding zeros to the end of that number. So here I've moved it 1, 2, 3, 4, 5 times, but I'm not going to actually write that decimal down, because if I did, that would make these zeros sig figs, and they couldn't possibly be sig figs if we didn't include them originally in our number over here. So we just want this number to be 186,000, no decimal at the end, and that is our standard form, our standard notation for this scientific notation number. Doing the same thing over here, we're going to move this decimal 7 times, but because that's negative there, we're going to move it in a direction that's going to make our number smaller. So I'm moving it to the left because 0.5 is smaller than 5, and I'm only moving it once past that 5. Then the next 6 times I move it, I'm going to be adding zeros. So I'm actually just going to start by adding those 6 zeros and then writing down all the rest of the sig figs that started in our base, including this final 0 here. If we kept it in our scientific notation, it's a sig fig, and we should keep it in our standard form number as well. So go ahead and do your best with this one. Notice that we're going to be moving the decimal 2 times, and that's a positive exponent, so we're going to be moving it kind of like what we did over here, but because we have so many numbers already, you probably won't have to add any zeros. So once again, give this one a try. I don't want to see it blank, but we can start class by going over these ones that I've left for you to do if you're uncertain of the answers, and make sure that you're on the right track. Hope you have a great weekend. Bye.